I'm ready to go.
Mm-hmm. All right.
All right. Uh, so let's get started. So thanks for having me give this talk. So I remember that. So this is I'm going to talk about the second series of work in Multicore OCaml. Essentially, I'll talk about it more, but this is the paper that got accepted at PLDI. This upcoming PLDI. And I remember last year, ICFP, we had another paper about Multicore OCaml. And the first thing that I saw that was picked up was a talk at JetBrains about parallelism and Multicore OCaml. That was very nice to see. Um, I think getting visibility for this sort of work is always great. And yeah, thanks for inviting me to give this talk now. Thanks to how we are doing talks these days. So today, what I'm going to talk about is what I call as effective programming in OCaml. This is just a play of words. As you will see, we have a lot more going on. So I'm Casey. I'm Casey Sivaramakrishnan, but yeah, the last name is a mouthful, so people call me Casey. I am an assistant professor at IIT Madras. I also work as part of the OCaml Labs initiative. So we work on the OCaml programming language, but also tools around OCaml. Um, so we are trying to make OCaml programming experience better. So that's OCaml Labs' um, agenda. And yeah, we sort of work both on the compiler and the tooling aspects. So the project that I work on is called as Multicore OCaml, as you would have expected. So the point of Multicore OCaml is to add native support for concurrency and parallelism to OCaml. So OCaml is one of the few systems programming languages that doesn't have parallelism support, even though it has been around for many years now. And it brings some interesting challenges, right? So when you want to add a feature like parallelism into a language that is moderately widely used, right? There are large industrial users who depend on this language. Um, Several interesting questions come up. Preserving semantics of the language, can we do it in a backwards compatible fashion? Can we preserve the performance and so on? So all of these questions are what Multicore OCaml tries to answer. And over the course of, I believe, 7 years now, we have a very good idea that we can, in fact, um, have our cake and eat it too, right? So we can get multi-core parallelism into OCaml, and we can do it without losing sequential performance and backwards compatibility concerns. So what Multicore OCaml in particular brings is a native support for both concurrency and parallelism. And I define concurrency as overlapped execution of tasks in time, where multiple tasks context switch to each other and yield control. Whereas I define parallelism as simultaneous execution of tasks over time, right? And many languages mix these ideas up. And in Multicore OCaml, we've been very clear in keeping these ideas separate. And in keeping with this idea, what we've done is we have separate mechanisms for expressing concurrency and parallelism. For concurrency, we have what are known as effect handlers. And for parallelism, we have a separate mechanism called domains. Domains are sort of units of parallelism that map directly to system threads underneath. So that's not going to be the focus of this talk now. This was a talk that was given in your lab last year. This time, what I'm going to do is talk about effect handlers. So it's a cool feature. So let's motivate why we need concurrency at all, right? So the thing is, even though many languages provide a single mechanism for, they tend to mix up concurrency and parallelism, we can in fact separate it, right? But performance is just a performance, parallelism is just a performance hack. It is a way to make your program go fast, right? But concurrency is a program structuring mechanism. It sort of yields a new way of writing down programs. And in keeping with this fact, we need separate mechanisms. But as I mentioned, some some systems mix parallelism and concurrency. For example, operating system threads give you both parallelism and concurrency, but they are too heavyweight for concurrent programming. What do I mean by this? Imagine if you were to implement a web server, right? Even though OS threads give you this nice abstraction where you can sort of say, I'm going to have a thread per request. Spawning an operating system thread per request is a terrible idea. This particular strategy wouldn't scale. Nobody does this, right? And that's for a good reason, because the strategy doesn't scale. But as an idea, right, having a thread per request is very nice. And many programming languages do, in fact, provide separate concurrent programming abstractions. What they usually do is they provide them as primitives. They sort of expose it as a mechanism that is implemented by the language. And there are several different variants of this, right? They all sort of fit within a unified idea. So, for example, you have async await in JavaScript and Python. You have generators, again, JavaScript and Python. C++ has coroutines. C# has coroutines as well. There are lots and lots of different mechanisms. Right? And often what languages tend to do is they sort of end up having all of these mechanisms and more, right? And the typical example, the strawman that we all sort of pick up is JavaScript. JavaScript has async await, JavaScript has generators, promises. There is also callback oriented programming in JavaScript. It is not uncommon to see a single JavaScript framework use any of these mechanisms in combination. Right? I mean, this is this sort of a way of treating similar looking mechanisms using different but incompatible interfaces is sort of not great, right? So, okay, given that state, what is the concurrent programming landscape in OCaml? So as I mentioned, OCaml does not have native support for concurrency. Does that mean that we cannot write concurrent programs in OCaml? We can. The way we do it in OCaml, the typical way to do it is to use a concurrency library, such as LWT and async. These are the two popular concurrent programming libraries. At the end of the day, all they let you do is to write callback-oriented programs, right? Using nicer syntax. They are an encoding of Poorman's concurrency monad, and they expose monadic syntax. OCaml now also has some syntactic extensions to make this look nice, right? But at the end of the day, all you're doing is callback-oriented programming. And even though we tend to use monadic syntax, none of these libraries are actually monads. They do not satisfy monad laws. So essentially, you're back to the basics, right? You're just writing callback-oriented programs. What is the downside of this, right? It's okay. We've built these sort of programs for many, many years now. Is there any downside to this? Yes, there is. It suffers all the pitfalls of callback-oriented programming because you're essentially writing code in a handwritten CPS style, right? So you're sort of saying, okay, here's the computation. When it completes, attach this callback to this. When that completes, attach this other callback. You are no longer using the program stack to run your program. Your program stack is now sort of in this weird CPS style. And as a result, what you cannot do is you have no backtraces because your program stack is now in the wrong direction. It's full of callbacks, right? You cannot use inbuilt exception mechanism because if you throw an exception, it goes to the wrong place. You have to use monadic syntax, right? I think people are used to monadic syntax in OCaml for a long time now, but in a language which allows arbitrary side effects, using a monad just seems a pity, right? And the difficulty is that unlike Haskell, OCaml does not have higher kind of types. So you cannot take two different monads and put them together and do something interesting, right? So you have to break it apart, include both of the monads. You have to do lots of ugly things. This is not a composable way of writing programs. Because of this monadic syntax, if you want to use LWT or async, any interesting part of the program will also have to use monadic syntax. It is just infectious. It sort of spreads all over the code, and there is this dichotomy now between two libraries. So you either choose the LWT camp or the async camp, right? OCaml has this two different bits which you cannot mix them together. This is all very unfortunate, right? And in terms of performance, because you are using callbacks all over the place, you end up allocating too many closures. So OCaml is a reasonably fast language, but it is not, in terms of optimization, it doesn't go very far, right? So it doesn't optimize for inlining closures and defunctionalization. All of this is not done. So you end up using a lot of memory on the heap, much more than you would need to. When you're doing IO, that probably doesn't matter, but we've seen programs where the memory pressure just kills the IO throughput. So there are lots of reasons for not doing callback-oriented programming. Right? Again, we are not new here, right? So if you sort of look at the landscape of similar languages, I picked Go and GHC here, but I can also bring in other languages to this discussion. But these languages sort of give you better abstractions. So Go, for example, has Go routines. GHC has threads, right? So these are lightweight language level threads, which are cheap to create. You can have millions of threads alive at the same time. And there is a separate mechanism to map these lightweight threads onto the number of available cores. Right? So this mechanism is great. So when we are thinking about what concurrency mechanism that we want for OCaml, we were sort of looking at lightweight threads as a mechanism, right? So the initial question that came up was, should we add lightweight threads to OCaml? And this was around 2004, end of 2014 when I joined Cambridge. And at that point, we came to know of a new mechanism that sort of gave us a way out of all of this, but also achieves much more. And that mechanism happens to be effect handlers. So effect handlers are, so the way you can describe them is they are a way to program with user-defined effects in general, right? So just like how monads let you do simulate effects in a pure language, effect handlers also let you do that. They were first introduced by Gordon Plotkin and Mattia Pretner in 2009 paper, and the ideas have been floating around for a while. And because we were on the market for some mechanism to express concurrency, which is also an effect, we sort of picked up effect handlers. And what effect handlers let you do is the cool bit that effect handlers let you do is they serve as a modular basis of all known non-local control flow mechanisms, such as exceptions, generators, lightweight threads, promises, asynchronous IO, and coroutines. And the way to read the statement is that if you put in effect handlers into your language as a primitive, then all of these mechanisms could be implemented as libraries. And they tend to be modular as well. So if a library implements exceptions using effect handlers and generators, another library implements generators using effect handlers, you can use them in the same program, and the program would compose together nicely, right? So this is the modularity aspect that effect handlers bring you. I will discuss more about this during the talk. But what really interested us towards effect handlers is that operationally, all they bring in is they give you a nice way of doing first-class restartable exceptions. Right? So we all understand exceptions. What if I mean the simple idea is that when you raise an exception, you unwind the stack. What if you are able to go back to the position where you raised the exception, but also make this ability to go back a first-class value, right? So that you don't need to immediately go back. You can save this ability to go back to a point in some form, right? As a first-class value in the program. Save it somewhere, you can come back to it later. This is all you need for expressing all sort of non-local control flow mechanisms. We will see this through the talk, right? And similar to exception handlers, there is this notion of performing an effect, performing a user-defined effect, which is separated from handling it, which is expressed by effect handlers. So the analogy that I would like to sort of start off with is think about exception handlers, which we know how exception handlers work, and we sort of extend that to effect handlers. And because of this analogy, we sort of effect handlers tend to look very similar to how exception handlers are encoded in OCaml. So if you are not aware of OCaml, I will run through this example step by step. So just like exception declaration, we have an effect declaration. This declaration says E is an effect, and what it says is when you perform E, you get string value as a result. Right? This is different from exceptions where if you raise an exception, nothing comes back, right? So, but the type here says that if you perform E does not take a parameter, but when you perform E, it returns a string. And we have this notion of computations in effect handlers, which are run within a handler, right? These computations are run in the context of a handler, right? And the computation itself may perform the effect. So perform is a keyword now. Actually, not a keyword. It's a standard library function which allows you to perform an effect. And the effect of doing a perform is that it suspends the computation, right? The computation here is this comp function. It suspends execution of the computation and gets you a delimited continuation at the matching handler, right? So we perform E. I'm handling E. When you handle exceptions, you just get the exception and whatever value the exception carries. Here, additionally, we get this continuation. This continuation is a delimited continuation. What do I mean by this? This captures the context that is the continuation from the point of perform delimited by this matching handler, right? So it actually represents, you can sort of imagine this to be just a dynamically defined function, right? So delimited continuation, unlike undelimited continuation, actually return you a value. I mean, this is the real, this is where the real power of effect handlers come in. This particular delimited continuation primitive, right? You have the continuation at hand. So what can we do with this continuation? You can continue, you can resume the suspended computation using this primitive called continue. So this continue primitive takes the continuation and the value that you want to resume your computation with, and the computation resumes with that value, and you run to completion, right? In this example. So okay, so this is just the syntax. Let's actually run through this example step by step. And the point of doing this again is that I'm going to show how the runtime system implementation of effect handlers also works, right? So on the left, I have the same program as earlier. My program counter is just before entering the computation. On the right-hand side, I have a representation of the stack, right? So the representation that I'm going to show is going to closely mirror how we implement effect handlers in Multicore OCaml. So when you first enter the computation, we actually allocate a very small piece of stack on the C heap, right? And we now say this is the piece of stack in which this computation function comp is going to run. And we establish a pointer, parent pointer from this new piece of stack to the parent. And the other thing that we do with this piece of stack is that we have this handler here. We also associate this handler with this piece of stack. And at the runtime, we call this piece of stack along with the handler as a fiber, right? So whenever you sort of enter the computation, you allocate a new fiber, and then run the computation in that stack space, right? So this stack space is allocated and is dynamically grown. So it starts off very, very small. It starts off at 32 words. And as we end up using more space, we tend to grow this, right? So that's the intention there. So let's continue with what will happen. So we now continue with this computation. We print 0, and then we are now just before performing, right? As I mentioned before, we have to suspend the computation and then capture the continuation. We have to sort of verify the continuation in this K. And the way we do that is we first allocate a one-word continuation object on the OCaml heap, make it point to the current fiber, right, which is the comp fiber. And we dynamically search for the matching handler that handles the effect that is being performed. In the simple example, the innermost one handles it. So what happens here is that we set the stack pointer to the matching fiber, right? And then our program counter moves to the body of the handler. We are going to execute the handler, right? And now what has happened is that we are going to execute whatever computation is in the handler, and we get this continuation as an argument to this handler. So observe, the thing to observe here is that capturing a continuation does not involve copying frames, right? It ends up allocating a single word object in the minor heap, which is very fast. And then we just point to that fiber. We can do this because we've already sort of split the stack into small chunks, right? At these delimitations, which are essentially effect handlers. So capturing a stack does not involve copying frames. And then we continue executing the handler computation. So it prints 1. Now we are at continue. We need to go ahead and continue this continuation, resume this continuation with the value 2. The first thing that happens here is we erase, we sort of set this continuation to null, right? So it no longer points to this computation. And the next thing that we do is we attach the continuation to the current stack. So, and then we set our stack pointer to the to where the continuation is suspended. So we are back at where we are. And another thing that has happened is that this continuation no longer points to comp. The reason to do this is that our continuations are one-shot continuations. So you can only use a continuation once, and this is necessary because we are not copying our frames over. So when you capture and resume continuations, we are not doing any sort of frame copying. Our use case is concurrency, right? If you look at the use case of concurrency, there is rarely a case where you need to resume a particular continuation more than once. Of course, there are use cases where you need to resume continuations more than once, probabilistic programming, backtracking, search, and so on. There we provide a primitive in order to explicitly copy a continuation. So we make a sort of this pragmatic decision to say we are going to optimize for concurrency because that's what we want to do, but we can also encode multi-shot continuations by explicit copying, right? So now we resume back, we resume with 2, so we print 2 here, and then we are at the stage where the computation is going to end. So what do you do when you end the computation, right? So this is just like returning from a function. So your stack pointer comes back to where it left off because we resumed, because resuming a delimited continuation is like calling a function, you return to the point of resumption, and then you execute the rest of the computation at that point. But observe that I've sort of thrown away this comp, right? So when this computation actually returns, we free the memory that we allocated for this particular fiber, right? So we malloc when we enter the computation, we free it when we return. So the garbage collection is very simple in our case. And yeah, we print 4 and that's done. So that's the execution of, stepping through the execution of this particular example. Okay. Handlers can of course be nested, right? So just like exception handlers, effect handlers can be nested. I have 2 effects here, A and B, both of which when perform return unit values. So what I have here is a function foo, which calls the computation bar in an effect handler which handles A, and bar in turn calls runs the computation bas in a handler which handles B, and bas performs A. So just before performing this particular effect, our stack looks like this, right? Because we've had 2 effect handlers, each one is separated out in space like this with parent pointers between them. When you perform this effect, we have to dynamically search through each of the matching handlers, right? So, and what would happen is that you would find that A is the matching handler, our program counter goes to the that particular closure, and our stack pointer now goes all the way back to foo. And the continuation that we capture includes both of these fibers, right? And the fiber for bas that was allocated here, and the fiber for bar as well. So our continuations include multiple fibers, right? We do have a linear search through our handler stack. So if you have many handlers, you have to linearly search through each one for the matching case. But this is fine. In practice, we see that our handler stacks are very shallow. So this is not. There are lots of interesting work now, which is trying to statically find out where is the matching handler and directly jump to it. But for our use cases, which is concurrency, linearly searching through, we have one or two handler stacks in practice, and dynamically searching through them is not the bottleneck for us. So that's the reason why we do a linear search. Okay, that's all fine. So I've shown you how these things work. What can I build with it, right? What does this actually enable? So everyone's favorite example is building lightweight threading, right? We said we wanted to start off with building lightweight threading like Go and Haskell. We should be able to do that, right? So here is a very simple example where I'm going to build lightweight threads with only two primitives. So I can fork off a thunk, which is supposed to execute concurrently, and I can yield, right? Which yields control to another lightweight thread in the scheduler. So correspondingly, I implement declare effect fork and yield, right? Fork takes a parameter, which is a unit or a unit thunk, and which when performed returns a unit value. Yield does not have a parameter, which when performed just returns a unit value. Okay, so that's the declaration. Observe that the fork and yield says nothing about the scheduler queue itself, right? The scheduler itself. A scheduler could be FIFO scheduler or a LIFO scheduler or a hierarchical scheduler. It doesn't matter. So this is sort of separating the concerns, right? The policy from the mechanism. So I just want to perform these effects. I don't care how you perform it, but it better be the case that it is implemented according to whatever type signature is given here. That's all the constraint is saying. The main workhorse in this particular implementation is the run function, right? Run function sort of wraps around all of the computations which might perform fork and yield and actually handles fork and yield. So it runs the main computation. We assume that there is a queue of continuations, right? So this is just a OCaml queue that's sitting there. I'm not representing it for lack of space. And what do we do in this in this run function? We call spawn on this main computation. Spawn itself takes a computation f, right? And it runs this computation. It's just a thunk. It runs this thunk in an effect handler. We call this an effect handler because it has effect patterns in the match cases. So just for folks who might not be aware of OCaml syntax, OCaml overloads the match with syntax. So you can of course match on values, but you can also have exception patterns in the same match width. So you can write exception E, then do something. The idea is that if it returns a value, you can pattern match on values. If it returns an exception, you can pattern match on exception. You're sort of extending the same idea here with effect patterns. So the idea here is this, right? So if this computation F, when run, returns a unit value, I just go ahead and call this run next function, which is going to pick up the next thread from the scheduler queue, right? When I say thread here, it's just a continuation. And if there is a continuation, I just continue this continuation with a unit value. Otherwise, this computation is done. There are no other threads that are left on the scheduler. So the whole run function is done. So I just return a unit value here. This returns the unit value. We are done. Instead, right, this particular computation can also perform the effects that I've written down here. If it performs an yield effect, I pattern match it here. And the continuation that I get here is in fact representing the lightweight thread. The context, all the context that is necessary for this lightweight thread. I enqueue this continuation into the queue, and I just call run next to run the next available thread from the scheduler. Instead, if you are performing the fork effect, observe that fork takes a parameter, which is a thunk that you want to fork off to run concurrently. So I take that f. I get a k, which represents the current thread. I enqueue the current thread into the queue, and then I recursively call spawn on f. And all this does is that this also spawns of f as a separate thread with its own handler, which is supposed to handle the effects that are performed here. So this is the entire implementation of a very simple lightweight threading system, right? And you can sort of wrap this in a nice looking function, right? So you can say fork is a function that takes a tongue and simply performs the fork effect, and yield is a function that performs the yield effect. So what do you get as a result? So of course we've defined that. So here is a nice looking program that you can write, which you cannot do today in OCaml, right? So it does something very simple, right? It says there is a main function that forks off two threads. Each of the threads prints a message, yields control, and then prints another message. If you run this program, if you run this main function, the output you will see is 1A, 2A, 1B, 2B. And the reason is that you first prioritize running this one, right? And then it yields control. So you go back to the main thread, which forks out the second one. So you print 2A, 2A is printed, which yields control back to the first one, which prints 1B. And when that completes, the only thing that is left to do is print 2B. So that is printed as well. Right? So very simple example. But the main takeaway here is that the code is completely in direct style, right? So there is no monadic use here. So you could write similar looking program using LWT racing, but you would have to use a monadic syntax. Observe that all of your code still looks as if it is doing direct style call, but we get the benefit of concurrency. And the user code itself says nothing about effects, right? There is no perform, there is no effect handler, there is nothing. Everything is hidden behind this nice interface, right? So as far as the user is concerned, it provides a very simple, straightforward looking library. Right? So this is a very simple example that we can extend to do all sort of concurrent programming. Right? Let's do something different. So um, I said effect handlers are the modular basis of all sort of non-local control flow. And another key example that people use is generators, right? Generators are these mechanisms which allow you to do non-continuous traversal of a data structure by yielding values, right? And generators are typically given as primitives in JavaScript and Python. Here is an example of a generator in Python, JavaScript. So here is a function generator, and when you use generators in JavaScript, you have to mark those functions as function star. What this tells the VM is that this particular function can yield values. It can suspend computation, right? And the way you yield values is using the yield keyword. And what this generator does is it first yields the given argument, and the next time it yields the given argument plus 10, right? And here is the way you would use the generator. When you call the function, what you get back is the generator object, right? And this object has a next function, which you can call to get the values on demand, right? So I get the next value and dot value because JavaScript. I print that value. The first time you get it, you get 10 thanks to this yield, and the second time you do it, you get 20 out, right? So this is useful. I don't know whether you've read this nice blog about what color is your function, right? So whenever you tend to write programs in a asynchronous fashion in a language, and you sort of bake it into the language, your language sort of splits into two worlds, one asynchronous world and a synchronous world, right? And the asynchronous world here is function star functions. So in JavaScript, any function that can yield has to be a function star, right? If the generator calls another function that is going to yield, that function is going to also be marked as function star. And I've done some, I mean, this is like very non-scientific benchmarking on a particular VM, right? Function stars are around 3 to 10x more expensive than just calling regular functions, right? So, yeah, and then you have to call this function differently, right? So you can call this function, but you have to use dot next and so on. So this occurs everywhere, right? This is not just unique to JavaScript. Even OCaml, right? If you want to encode asynchronous functions, today the only way to do that is using LWT racing. And there you have to sort of use this monadic composition operators to extract values from asynchronous functions. This sort of problem is pervasive across various languages, right? Um, and And what effect handlers in OCaml lets you do is to sort of erase this dichotomy at the surface level. There is still going to be some um, overhead, performance overhead. We'll come back to that later. But at the surface level, this dichotomy is no longer going to be there, right? I'll sort of try to convince you that this is in fact the case. So what we're going to do is something fun, right? So instead of writing down generators for each of the data structures, if you can give me a container or a data structure, and then you just write down the iterator function for that particular data structure, I will automatically derive a generator for you, which does something similar, right? With which you can traverse the data structure on demand. In particular, this is what I'm going to do. I'm going to, this is a functor, right? And just reading it in plain English, what this says is, assume that there is a container, right? Which has some alpha values, right? And you also give me the iterator on this container. So this is going to take a higher order function. The expectation is that this higher order function is applied on every value in the container, right? And then it does nothing and returns unit. What I will, this functor, what it promises to return is to return you this generator function, which when applied on the container, the same container, it is going to return you the equivalent of the next function that we saw in the previous slide, right? What this is saying is that I'm going to return you a function which you can call with unit values. It keeps returning optional values until you completely traverse this data structure, right? This is what this particular implementation is going to provide. The actual implementation, entire implementation is this. It doesn't matter. I mean, I don't want you to focus on the details here. The main takeaways are that we use effect handlers internally. We declare an effect called yield for this particular type, right? And at every step of the iteration, what we do is that we perform yield on that value that we get using iteration. So this suspends the computation. We have a handler which handles the yield value and then prepares the next function, so that when you call this next function the subsequent time, it is going to resume the computation, right? So that is done here, and then it returns some v. Details are not important, right? But what you should perhaps take away is that this is sort of mixing lots of interesting features of OCaml, right? It has functors, it has locally abstract types, it has local modules, right? This is a local module. It has recursive values. This is the step is a recursive value. You can mix all of these features together along with the and of course it has references as well, side effects here. You can mix all of these features together with effect handlers to achieve something very nice, right? This code does a lot of things, but as far as the user is concerned, none of this matters, right? Only the interface matters. So here is how you actually use this interface. So here is the make gen for a list, right? So I say this alpha t is an alpha list, and this iterator is a list iterator. I get this generator for a list now. What can I do with this? I can call l.gen on this list 1, 2, 3, and I get this next function. If I keep calling this next function, I get values 1, 2, 3 successively, and then none. Right? You can do the same thing on any data structure that you can imagine, right? So here is a binary tree. Here is a iterator over the binary tree that does in-order traversal, right? Iterating left, then the value, and then iterating on the right. Here is I am deriving a generator using an iterator for the tree. The type is the tree, and the iterator is this iterator. For the sake of an example, here is a neat trick to make a complete binary tree of depth n using n O of n space, right? It creates a DAG, but that doesn't matter. So it creates a complete binary tree of depth n. You just give a make of n, it gives you such a tree. So when you do make 2, this is the numbering that it also does. So you have 2 at the root, 1 and 1 at the leaves. So now you can just call t.gen on t, right? And because the iterator does in order traversal, you get 1, 2, and 1, and none. Right? So the takeaway I want you to sort of get from this is that none of this actually talks about effects or handlers, right? From the user's perspective, this provides a very clean interface, right? So that's what I want you to take away. Okay, so those are the two examples that I had, right? So this is all looking nice. Okay, this looks like a fun little feature to add to the language. But we are in fact working in a very real language that has been around for 25 years, right? So we have to carry the baggage of legacy code. And this is where I get into some details, right? So we have huge retrofitting challenges. And this is the reason for writing these two papers, which dealt with retrofitting challenges. We have millions of lines of legacy code, right? And none of this code is written with non-local control flow in mind. All these functions are written with the expectation that there is no non-local control flow except exceptions, right? Exception mechanism is the only non-local control flow in these programs. And these programs tend to guard against exceptional behavior, right? But otherwise, they don't care about anything else. So we are going to add this feature. As you saw, the fact that you are using this feature is not visible at all, right? So adding non-local control flow, these sort of non-local first-class non-local control flow brings in interesting challenges, as we will see in certain examples. But the takeaway is that if I tell you that I will give you this feature, but you have to refactor your sequential code, the cost of such refactoring is going to be prohibitive, right? And OCaml is sort of a language that is very conservative in how it evolves. And if there is something that we are going to add that sort of breaks existing programs, that's going to be a no-no from day one, right? So we've been very, very careful to make sure that whatever we design, we keep backwards compatibility before fancy new features, right? So our design is sort of carefully laid out so that we preserve the semantics of sequential programs as they should be. So one typical example is that systems programming, right? OCaml is used for systems programming. What do you mean systems programming? Manipulating things like files, sockets, buffers, etc., etc., etc. Right? So OCaml tends to be heavily used in this space. And as I mentioned before, right, when people write OCaml programs today, they know that they have non-local control flow, and the only source of non-local control flow is exceptions. When you call a function, your function can return with a value or return with an exception. They write code so that it works against exceptional behaviors, right? So we tend to write it in defensive style so that when an exception is thrown, we clean up resources. So here is, say, a copy function, right? This is not the best way to write copy, but anyway, so it gets the point across. So what this does is it takes an input channel and an output channel, and it calls this loop. At every iteration of this loop, it reads an input line, and then it writes that particular red string to the output channel, and then keeps looping, right? And exceptions are very, very cheap in OCaml, and they are used pervasively. They are even used in this function to signify termination. When the input line actually sees that it has reached the end of file, OCaml's inbuilt input line function raises the end of file exception, right? And the standard way of dealing with this is you handle end of file, you close the input channel and output channel, right? So this is what you do that terminates the copy loop. But it is also the case that input line and output string can raise other exceptions. In particular, one example is they can raise sys error exception if the channel happens to be closed concurrently elsewhere, right? So, and this particular code is written being aware of that. So what it does is it handles all of the other exceptions. It calls close in and close out on both of the channels. Close in and close out are no ops if the channels are already closed. So this is safe code. And because this is an exceptional condition that the copy function has not anticipated, it simply raises the exception so that the caller is going to sort of be aware of this, right? So this code is well-written code. It handles value return. It also handles exceptional return. Um, what we really like to do is magically convert this code to be asynchronous. There is a lot of code that is written in this style, right? So our hope is that we can take this sort of code, which is written with lots of thought, right, and make it work asynchronously. So here is how you might do it with asynchronous IO, right? So corresponding to the input line and output string, the input line and output string, I declare two effects inline and out string, which are parameterized with the exact argument types. And input line takes an input channel, and which one perform returns a string. Output string takes an output channel and a string, performs the output, and then returns your unit value. Right. So this is matching the built-in standard library functions in their types. Right. And you might implement those functions just like earlier. So input line function is just going to perform the effect input line, and the magic happens in the run function, right? So here is um, a very compressed way of representing asynchronous IO. What this does is you're going to run this computation again in a handler, right? If it returns a value, you just return that value. If it performs the input line effect, you sort of register somehow, right, this channel to be read for input, right? I'm not going to represent what it is doing. You can use libev, libuv, select, epoll, whatever mechanism you wish. I'm just going to consider this to be some function that does the work for me. And what is the interpretation of this k? This k is just the callback, right? This is the callback that you sort of resume when you successfully read a string from this input channel. That you do asynchronously. This is what you do when you sort of when the asynchronous IO successfully completes. You continue this continuation with that value, and that gets you back to where you were. And because we are suspending this computation now, I just call the run next function. Assume that the run next function was similar to what we had earlier. Similarly, we have for output string, right? Yeah. So when the asynchronous IO completes, we will continue this. But observe that the earlier program, right, really expected end of file exception to be raised when the input reached end of line. And if there were any other condition, it also expected this particular function call to return an exception. With the mechanisms we've seen so far, we can only return values we can only resume continuations with values. But what we need in these cases is we need to resume the continuation with exceptions, right? And by which I mean you resume the continuation by raising an exception at that point, right? So how do we represent that? In order to do that, we introduce this primitive called discontinue. It's very similar to continue. All it is doing is that you can take this continuation and you can give an exception, and what it does is it resumes the continuation by raising an exception at the point of perform, right? And this is useful for us because with this particular discontinue, we can actually get the same semantics as what we would expect for that original copy function, right? So that's an additional thing that we had to do. And this asynchronous IO scheduler, what it will do is, if it encounters exceptional cases, it picks the right sort of exception and then discontinues that continuation with those exceptions. Okay, so that was a extension we had to do in order to deal with exceptional cases. The other one is linearity, right? So when you program with resources are resources such as sockets and file descriptors are linear resources, right? So you create them and destroy them exactly once. And the guarantee that you have today when you call OCaml functions is that if I call a function, it returns exactly once. It will return with a value or it will raise an exception. And defensive programming style already guards against both of these, right? It guards against exceptional cases. But with handlers, effect handlers, what happens is that this is no longer true. Our functions may resume at most once. This is bad because you can call a function. That function may perform an effect. Your control sort of jumps all the way across this function, right? And in the handler where you handle the continuation, you can just drop the continuation on the floor. You can just not resume it. In which case, you may leak resources. This breaks resources like resource safe legacy code. So here is an example, right? Here is a well-intentioned little example where I have this effect E, which when performed returns your unit value. Foo is a function that just performs E. Bar is this nice function, right? Which says for some reason I'm going to open this input channel, right? I'm going to keep this input channel. I'm going to call foo. Um, bar knows nothing about foo, right? The only guarantee that it knows about foo in today's OCaml is that I can call foo. Foo will either return with the value. If it returns with the value, I'm just going to close the input channel. If it returns with an exception, I'm still going to close the input channel to make sure that I don't leak resources, but I raise the exception again, right? So this is sort of looking fine in today's OCaml. You might imagine this function to be a proxy for all of the code that are well written in OCaml today. It doesn't know what this foo function is, right? The foo function might be a higher order argument to bar, right? So it has no idea what that function is. Foo happened to perform E, and in the handler, which is in BAS, I call bar computation. I handle the effect E, which is the effect that is performed here. I don't bind the continuation, and I just return this unit value. Because I don't resume the continuation, I leak this IC, right? And the problem to and the observation to take away here is that this is no fault of this bar function, right? The bar function is not at fault. It is actually the BAS function that is at fault, but it is leaking resources, right? So there is no easy answer to this, right? So if you have linear types, I think we can encode this as a safety property that is statically captured, but we don't have linear types in OCaml. So what we assume is that if you capture a continuation in OCaml, you resume it exactly once, either continue or discontinue. So you can call this a downside of our design. We've also explored the possibility of installing a finalizer on every capture continuation so that we unwind the stack explicitly, so that we may allow IC to be released, right? We just raise an exception which is not one of the known exceptions, in which case for well-written code, those resources will be closed. But it turns out that doing that is on reasonable programs, it is around 2 to 4x more expensive because we are using the finalizer to clean up resources for every capture continuation, and that is not worth it. So we make a pragmatic trade-off saying that we assume that the capture continuations are linearly used. Okay, so that was about backwards compatibility. The other thing that many research languages tend to overlook is things like backtraces, right? OCaml produces excellent backtraces, and it has good compatibility with GDB, LLDB, perf, libunwind, etc., etc. So it produces well-formed. It has enough dwarf magic encoded so that it produces proper-looking backtraces, right? And this is useful. I tend to use because I work on the runtime. I tend to use backtraces, GDB, RR, and other tools pervasively. And because we've sort of messed around with our stack, right? Our stack is no longer a contiguous stack. It is sort of split between multiple places. This makes backtraces interesting to get. So the thing that I want to mention is that Dwarf is a Turing complete language, right? So Dwarf is hilariously interesting. It's you can do whatever you want in Dwarf, and C++ uses C++ exceptions uses Dwarf, right? So there's a nice paper which says that the exception unwinding mechanism in C++ is an attack vector, right? Somebody can just attack Dwarf code and they can take over the program. But Dwarf being Turing complete means that we can in fact unwind across fibers. For example, this is the same example as what I had shown in the previous slide. And the stack appears like this, right? Bash is run in the first fiber. And because I have a handler here, right? So bar and foo are in this second fiber, right? So stack grows down. What we end up doing is that we have some bespoke dwarf bytecode for unwinding our call stack across these parent pointers. And we also have similar situation for callbacks into OCaml and external calls. And we have to write some hairy looking bytecode, but dwarf bytecode, but this is only once, right? And we verified this bytecode with a nice tool that is available today, thanks to Stephen Kell, who is a lecturer at University of Kent. So they produced a nice tool that can verify the validity of your dwarf bytecode. So we verified with it, and we are reasonably confident that our dwarf unwinding works. So what do you get as a result, right? So if you run this program, you set a breakpoint at perform here in LLDB, and then you get the backtrace. You can get all the functions across multiple fibers, right? So we get foo, we also see bar, right? And there's also bas here. And this run stack is an internal function that sort of sits at the effect handler delimiting area. So you can actually get the entire backtrace of all of the functions. This is quite useful for backwards compatibility. So today your programs work with LLDB. They will continue to work with um, effect handlers in, right? Okay, so that was about retrofitting. I want to say a little bit about static semantics. So we don't have effect safety. So many research languages that introduce effect handlers, they have the static guarantee that if you write a program that uses user-defined effects, they ensure that all of the effects are in fact handled, right? So we don't have that guarantee. This requires an FX system, and the FX system is in progress. So we are, in fact, it's an open problem. So because OCaml is a language that has lots of advanced features, right? Abstract types, modules, and generativity, and yeah, there are a number of features that sort of conflict with implementing an FX system for OCaml. It's not impossible. We have prototypes that are currently in development, right? But it just is a very different looking language at that point. So we have to be really careful so that programs that continue to work today continue to work with OCaml with effect handlers, effect system, right? So we are doing that. It will land eventually, but we don't have effect safety today. And when you perform me at the top level, all we do is we raise unhandled exception. So we sort of say, okay, this is unhandled. FX system is in the works. There are lots of nice languages that have expressive FX systems. Coca, F, Lynx, and Helium are all a few examples. We are in fact working on an FX system for OCaml. The thing that we are trying to do is to track not just user-defined effects, but we are also tracking built-in effectful operations, including references, IO, exceptions, and so on. At that point, OCaml will become a pure language in the Haskell sense, right? Divergence is still allowed. So just to give you a sense of what it might look like, I mean, syntax is still in the works. Today, if you write this function, you just get a unit arrow unit as a type. You don't have any clue of what that function is doing. In this effect system enhanced OCaml, you will see that it takes a unit, returns a unit, but also performs the IO effect, right? So this is sort of what the future looks like. And we have ways of making sure that we can incorporate the usual MLI files. We can assign semantics so that they just don't break. They just don't all break when we add this effect system to language. But that's future work. That's not what I'm going to talk about today. So we have a dynamic semantics for this language in the paper. So the dynamic semantics is itself described as a small step operational semantics as an extension of the CEK machine from Palaisen et al. You might ask why? Why bother with dynamic semantics at all for this extended language? And the reason I wanted to do that is that our stack layout is much more complicated than stock OCaml. By stock, I mean OCaml today, right? In stock OCaml, when you get a backtrace, this is the backtrace that you would see, right? If you sort of have a bunch of external calls and callbacks, so you will have the C main function that calls into the OCaml main function. You execute some OCaml. You may call into C again using external calls. The external call can call back into OCaml. All of this runs on the same stack, right? They're all in the same stack. We know how these sort of stacks work. But if you do a similar thing in Multicore OCaml today, this is how the stack will appear to be. So we have a system stack where C functions are executed, right? As I mentioned before, fibers are allocated with very small space and they tend to grow. So what we end up doing is we insert stack overflow checks in the function prologue of every OCaml function, right? So this ensures that when we hit the stack threshold, we can double the size of the stack and reallocate it. We can't do that for C, right? C doesn't have stack overflow checks. We can't run C functions in these small fiber spaces. So we have a system stack where you will have the C main C function, which calls the main entry function into OCaml. This can have many frames, but it can also install an effect handler, which creates a new fiber. This fiber can call back into C. We have to use the system stack again, right? This C function can again call back into OCaml. This creates another space for a fiber. So our whole stack looks very complicated, right? So the OCaml has an expressive mechanism already that tells you what happens with exceptions thrown from C. Now we also have effects, right? So we wanted to get an idea of how this works. So that's the reason why we have dynamic semantics. I can deep dive into the semantics in the remaining time. Would you recommend doing that, or would you recommend I go to the performance results? Any thoughts on that? I can quickly cover how we organize the semantics. Why don't I do that? I mean, performance is good, right? So let's do semantics. It's fun. Okay, so I just want to cover high-level things, right? So the main point of, can you see this? What I'm presenting? Yes, right? Okay, wonderful. So what is the purpose of the semantics? The purpose of the semantics is to help us model the interaction with the C and the OCaml stack in an interesting fashion, right? So we have a very simple language, lambda calculus extended with effect handlers. Um, we have integers, right? And we have two kinds of abstractions. And the intention is that we represent OCaml functions and C functions in the same language. You can arbitrarily call OCaml from C and C to OCaml. We want to show how the stack evolves as we do this, right? We have the usual lambda calculus abstractions. We have some binary operation to make the semantics more interesting, but that's not important at all. In addition to the usual lambda calculus expressions, we explicitly model exceptions and effects separately. So we use raise for exceptions. Raise takes a label and then some expression that is evaluate value. We consider in the simple example to be every exception also carries some value, right? We have the match with syntax, and each of these handler cases could be one of these things, right? So it must have a return case, right? So that tells you what happens when you return a value. It can have one or more of the exception cases that is handling exceptions and this effect cases, right? So the effect cases is the same as what we had seen earlier. So that it carries a label, right? Unrestricted label for naming the effect, the value that is carried by the effect, and then the continuation, right? And we have raise for raising exceptions and perform for performing effects, right? Okay, so that is the expression language. For the configuration, I think it is most useful to go from the top down. So our configurations are composed of three things. We have the terms. Because this is a CEK machine, we can have expressions or values, right? We have an environment that maps variables to values, that just maps variables to values. Oops. And then this is the interesting bit. We have a stack, right? Our stacks are either the C stack here, or the OCaml stack here. So the idea is this, right? So if you look at how we've organized our stack, we can have alternating C and OCaml frames, right? So I want to do something different when I'm in C or OCaml, and when you are in OCaml, you can have C frames underneath, and when you are in C, you can have OCaml continuations underneath. So we sort of can have multiple fibers underneath and C underneath again, right? So we have this alternating sequences of OCaml and C frames, and that is what this is intended to capture. The idea here is that C stack is very simple. It has a list of frames, right? It has a list of frames, and it has a OCaml stack that sits underneath it. The OCaml stack itself could be a empty stack, because if you are in the topmost C main function, then the OCaml, there is no OCaml underneath, so that is empty. Or the OCaml stack is a pair of continuation, right? I'll come back to what continuation is, and the C stack that is sitting underneath. And what is a continuation? A continuation, as I mentioned earlier in the interactive example, is just a list of fibers, right? So a continuation is a list of fibers. We use this triangle to represent a list to be distinct from this list here. So it is a list of fibers. What is a fiber? As I mentioned earlier, fiber is just a list of frames and the associated handler, right? The handler has a bunch of cases and the environment that is associated with the handler. So our continuation is just a couple of fibers, each one with its own handler, right? So that's the setup for the stack. And the interesting interactions all happen based on the stack. Let me quickly go through the important rules, right? So because we might have OCaml and C stack, the way we've sort of split this is that our semantics at the top level can take either an OCaml step, right? If the stack is OCaml stack, or a C step, right? To yield a different configuration. We have some administrative reductions. I'm going to skip this for now. Let me come back to it later. So here is all the C rules. So okay, so this is the C. So here is a rule which says, what should I do when I call a C function when I'm running C, right? When you just want to call a C function when you're running C, you just call that function, right? So the function itself is this abstraction that is sitting here with this value, right? I'm going to apply this function to this value. Because this is C, all I do is I simply now step to evaluating the body of this abstraction, right? Where I sort of extend the environment with x maps to v. That's the value that I'm applying for v. So this is the usual CEK semantics. And observe that the stack itself remains the same, right? So I'm going to sort of return a configuration here. So it leaves all of the frames as is, and the OCaml stack that is sitting underneath remains as is. The stack is the C stack. But if I'm calling an OCaml function, so what is the meaning of calling an OCaml function from C? It is calling back into OCaml. This is also what happens at the entry to the main OCaml function, but that's going to be just the same, right? So what is the semantics here? Because I'm calling an OCaml function, I need to convert my stack to OCaml stack, right? So again, this part remains the same. I'm going to evaluate the body expression, and then I'm going to extend the binder with this value, right? That's fine. I'm going to create a new continuation, right? And what is this continuation? I'm going to actually have a new OCaml stack. This whole thing is the OCaml stack, where the C stack sits underneath, right? This is exactly the C stack that I had at the point of call. That's a C stack that is underneath me. What is the continuation that I have now? The continuation is sort of the empty continuation, right? So there are no frames, and there is nothing interesting here. I'm not doing any handler operation. I'm not doing anything interesting with exceptions. So this just has a identity function. Sorry, identity case, right? So this return case is identity. It just gets a value, returns a value. The environment for this handler is empty. So this is sort of representing the empty continuation that I have here. So at the high level, what has happened is I went from C stack to an OCaml stack, where the C stack is now sitting underneath it. Similarly, you have to do the reverse when you return. So when you return from C to OCaml, there are no frames here. I have a OCaml stack that is sitting underneath. All I do is I end up executing the my stack becomes the OCaml stack. I'm sort of returning to OCaml here, and let me come back to exceptions later. And similar thing happens for OCaml calling OCaml functions and OCaml calling C, right? So just to maybe point out the first thing, right? Because OCaml stacks are composed of continuations, right? What we have is a continuation, and the continuation itself is a list of fibers where each fiber has a list of frames. Our evaluation in OCaml always happens at the topmost fiber, right? So if you sort of compare this to this one here, I always evaluate at the topmost fiber. This is the topmost fiber. The rest of the continuation is here. And when you call OCaml, you just do the call as is. You do the reduction in the topmost fiber. The rest of the continuation remains the same. When you call C, this is the external call. This is OCaml calling into C, and the way we model this is we now introduce a C frame, right? The stack becomes a C stack with no frames, and the OCaml frames, the continuation that was underneath, the whole thing becomes part of the continuation here, right? So that's the interesting bit. This sort of models the transition from C to OCaml and OCaml to C, right? So that's the first thing. Let me quickly tell you what happens with the handlers, right? That's the interesting bit here. So yeah, so when you reduce this match with function, we introduce a new fiber, right? So we introduce a new fiber where there are no frames currently on this fiber. The handler is this H here, and we take the environment at that point, and that becomes the environment for the handler. The continuation, we just cons this new fiber to the front of the continuation, right? And we start evaluating the body, right? So if this performs an effect, then that is handled by this handler here. That's the intention. So here is let's actually look at how, say, exceptions are handled, and then we can go back to FX. So if I am in a state where I am throwing an exception, raising an exception, and I have a handler, right, that is underneath me, and I'm sort of ignoring all of the other frames here, right? And there is a value that is being passed as part of the exception as well. If the handler has a matching case for the exception, observe that I'm sort of raising the exception L, and the condition, side condition here is that there is a case for handling this exception L. Then what I do is I have to evaluate the body of this exception, right? So I do that here, right? The thing that I've done is I've thrown away, I've actually unwound all of the frames here, right? So there were lots of frames here. I've sort of thrown all that away, and I'm actually at a stage where only K prime remains, right? When you throw an exception, you sort of unwind everything. And that is what I model here. And the body of the exception is what I evaluate here. With the, this binds the value to X. So I just extend the environment with that similar binding. So this is how we model exception handling. If you sort of Okay, so what is the other case, right? If the exception is not handled. So here is the case where the side condition is the handler, where I'm raising L is not part of the handler. You have to forward it to the, you sort of have to throw away this fiber and then forward it to the next fiber on the stack, right? So I'm raising an exception here that has a couple of frames. I may have more frames, which I'm sort of ignoring. There is a handler H. I don't care about the environment here because the side condition says that the handler does not handle this exception L. What I do here is I take the next fiber that is on this continuation, right? And I continue to raise the exception on this fiber. So I've sort of thrown away one fiber. I'm sort of forwarding the exception to the next fiber on the stack. Okay, so that is exception forwarding. How does effect forwarding works, right? So when maybe one thing to sort of look at is what actually happens when you call perform. So when you call perform, what do you have to do, right? You have to sort of what happens at runtime? We sort of create this initial continuation, and then we have to sort of grow the continuation as we either successfully match or move forward searching in our continuation stack, right? So what the way we reduce this perform expression is that we create an empty continuation. We mark this as effect, where the effect being performed is L. Here is the empty continuation, the same as what we had seen earlier. So no frames. The continuation starts off as just having an empty handler, right, with an empty environment. That is the continuation. So it starts off as empty. And what happens when you actually want to handle it? So here is what happens when you handle an effect. So the effect being performed is L. I have a continuation K, right? And that is the captured continuation so far. My handler H has is handling this effect, right? So effect LXR is part of this pattern. So what you do now is you have to sort of um, reify this continuation and provide it to the handler computation, right? So this handler is going to bind this continuation in R, right? And what is the continuation that we have captured here? It is everything that you've captured so far and the current frames in the fiber, right? So everything that is also there in the current fiber, so which is this psi here. So we sort of say we extend the continuation by appending the current fiber also to that. That becomes k double prime, right? And we sort of say your R, which is the R that we have in the effect pattern, is now bound to this k double prime, right? So that sort of reifies the continuation. The value that was sort of given as part of the raise is bound here in X. And then we evaluate this body of the handler E here. And what is the scope where we run this? We run it in the scope where we have the rest of the continuation. So our continuation is handled in a particular state. We evaluate it in the parent, right? And the parent is K prime. So that is how it is captured here. Maybe the one thing that we want to sort of capture is what happens when we when the current handler does not handle the effect, right? So this is we have to grow this continuation little bit. So here is the effect, right? So that I'm performing, and my handler here does not handle it. So that I capture as a side condition. My handler is not handling it. The fiber that is sitting underneath this one, under which I have the rest of the continuation, I have to somehow capture this continuation, right? This thing that I have to sort of wrap it up and then continue, try to see whether this fiber handles the effect that I'm performing. And the way I do it is this way, right? So I have psi HE here. So I sort of wrap up the psi HE and then extend the continuation that I built up so far, right? K here, extend that with this current fiber. So it's sort of extending that fiber. I sort of say I gotta call it k double prime, and now the continuation includes this fiber as well, right? And the effect that I perform here is k double prime in the fiber that is sitting underneath, in the hope that this particular fiber at least handles the continuation. So this is how we sort of start from an empty continuation and then slowly grow it up. And there are, of course, other rules. I think this captures most of the complexity of what we are trying to achieve. There are lots of side conditions about what happens when you perform an effect which does not have a matching handler. We raise an unhandled exception and so on. So this semantics is intended to capture all of that very precisely. But that's the overall picture. Okay. So yeah, given that I want to have some time for questions, I'll just summarize the results that we have. Okay, so let's skip that. This one. Okay, so here is an interesting benchmark that you might want to sort of take away, right? So what we've done is we want to keep the cost of installing an effect handler as low as possible. And ideally, what we want is this has to be as cheap as an on-tail function call. I mean, this is an optimistic goal, but that is what we want to do, right? These are not heavyweight threads. So installing an exception handler has to be really, really cheap. So this function itself is doing something very, very simple. So foo is a function that performs an effect in a handler that immediately handles E, which immediately continues with the unit value, and this whole computation runs to completion. There is nothing interesting happening here, except that I've annotated this particular example strategically, right? A, B, C, D, E. And why have I annotated this? So if you look at the sequence of instructions from A to B, that involves creating a new stack for this fiber and running the computation, right? And B to C involves performing and handling the effect, right? I want to perform the effect and I'm handling it here. C to D captures the cost of captures the sequence of instructions that are there while resuming a continuation, and D to E is when you complete a computation and you sort of free that stack allocated for the computation, right? So each of these instruction sequences involve a stack switch, right? So stack switch from main to this computation, computation to main, main to computation again, computation to main, right? So what I wanted to do is to measure the overhead of doing some of this. So I measured the overhead of doing this using Intel cycle accurate counting performance measurement. For calibration, memory latency on this machine was 90 nanoseconds for local NUMA node. So the time in nanoseconds was 23 nanoseconds for A to B, and then less than 15, around 10 nanoseconds for each of these other sequences, right? And this is really, really cheap compared to, I mean, if you sort of take memory access as a calibration point, right? So this is expensive because we are actually going and performing an allocation in using malloc, right? So you spend most of the time in the memory allocator. But typically, in many examples, we tend to go into the computation once, but switch back and forth many, many, many times. And one of the times is generators, right? So this is the same example as what we had seen earlier. What I'm measuring here is the performance of doing traversals on a complete binary tree of depth 25. I compare three versions here. First is the idiomatic iterated traversal. Second is the handwritten traversal, where I do CPS translation, defunctionalization by hand, removing intermediate closure allocations. This is the best you can do, right? And the last one is what I had done with the effect handlers. And this is the takeaway, right? So if you do iterator, you run fast because this essentially does not suspend the thread at all. If you do handwritten generator, you can get 3.7x times slower than this, but you get the benefit of suspension. With the effect handler generator, it is around 9.3 times slower than iterator. But the point here is that we are not doing any interesting work, right? I'm suspending and immediately resuming. If you have useful work, this overhead is going to be much smaller, right? And this is generic. It works across all sort of data types. This is specific to the binary tree. right? And just for a comparison, here is what the JavaScript does, right? Between iterator and generator is 90 times more expensive. So being 9 times more expensive, I would consider that as a win, right? And we've also compared against full-fledged web server. So this is really what we wanted to do. And it turns out that the performance is comparable to the libraries that we have in OCaml today, but also Go. We are very competitive against Go. If you can take Go as a comparison point, what we are doing now is to implement direct style interfaces for IO and the best in class, right? GCD for Mac and so on using effect handlers. Yeah, we are just kicking every comparable IO library out of the park with our performance. And the reason is that we don't have closure allocations. All of the code can remain in direct style, right? That's the takeaway here. We can use OCaml exceptions. We can do backtraces per thread. You can suspend the web server at some point and then get the backtrace of all of the ongoing connections. I mean, that's very cool, right? And I mean, GDB and perf continue to work. So more than the performance, these are the benefits that we care about. And yeah, that's all I had for today. I think I'm sort of took up all of the time, but I'll stop here for a few minutes for questions. All of this is open source. You can install it and play it. Yeah.
Hello.
Hi.
So,
Hi.
thank you for your talk. My name is Ilmir, and I am working on coroutine support in Kotlin programming language.
Mm-hmm.
So I have quite a few of questions for you.
Mm-hmm.
First of all, have you looked into how we in Kotlin support coroutines? No.
No, I haven't.
Uh, uh, I think you would be pleasantly surprised because we also use continuations as a primitive around our suspend functions, which are used for async await, generators, and coroutines.
Wonderful. Wonderful. Yeah.
And because we are working on JVM, we cannot just copy a hardware stack. So we had to come up with clever idea, which is essentially CPS transformation, but built into the language. And backtraces were also challenging for us.
Yeah, it's once you do CPS, you have to do all sort of games to get the backtraces back, right? Do you have backtraces in Kotlin?
Yes, we have.
Okay, wonderful.
We have, and I am very proud of this.
Yeah, I can imagine it must have been like moving mountains, right? So
yeah, exactly. So we just traverse continuation objects, which are like OCaml's fibers.
Right.
So we have multiple of them, and they form a single linked list.
But I think the distinction is that with the CPS, right? So each of the continuation objects will happen to have multiple frames, and then you have to traverse the continuation objects.
Yeah.
Here, the only thing that we have to do is we sort of okay. So we do it at the boundaries of fibers, not at every suspend point. Yeah. Okay. So similar. Yes. Okay.
So we also not on every suspend point, but between suspend functions, which are we're traversing call stack.
Sure.
And my a question for you: do you support some kind of structured concurrency where if one task in a tree of tasks fails, the other tasks are cancelled?
Yeah, so a really good question. So our strategy for all of this is to actually make it a concern of the library. So we have a library called EIO, funnily named from the rhyme, right? Nursery rhyme, EIO.
Yeah.
So we use the idea that I think F# uses. So we introduce cancellation contexts, which are essentially tokens, right? Where a thread can say, I'm going to be registered with this cancellation context, and you can cancel a context. And this sort of cancels all of the fibers, lightweight threads registered on this context. But we don't do this by default, right? We sort of have a IO library that where we implement this. We did do a bit of searching for cancellation, and that seemed like the cleanest abstraction for us. Yeah, F#. We just took it from F#. So they.
So you mentioned also multi-shot continuations. Do you have some kind of support so a user can access multi-shot continuation and revert to a previous state?
Yeah, so what we have is we have a function called clone continuation, which given a continuation returns your copy. And you just get a second copy, which is also one shot. So that's the way we expose it. But the thing with multi-shot continuations is it's just even worse than even worse in the presence of resources, right? When you call a function, you expect the function to the function may return more than once, right? So this is just bonkers, right? So I think this is the reason why we sort of relegated it to obj module in OCaml, which is the place where features that you shouldn't use live. But we have support for that. Implementing that was straightforward for us, and it is exposed to the user. But yeah, I don't have a good story for how to marry multi-shot continuations and resources, right? So
yeah, exactly. We also don't support multi-shot continuations officially, but unofficially we implemented a regex engine with them just in our spare time.
Yeah, very similar thought process. Yes.
Yeah.
It's just,
and the last question, you also mentioned, well, first a note and then a question. You mentioned what color is your function. Either it is an article or a paper, I don't remember.
Yeah.
We do color our functions in Kotlin. So suspend functions and ordinary functions are different. You cannot call suspend functions from ordinary ones, but you can vice versa. And we are going to extend this idea and introduce full-blown coloring. I don't know when, because it is just an umbrella around a lot of language features. Well, the idea is that there are several colors, and you have restrictions of what color can interact with what. And you said that you are going to implement event handlers in OCaml. Are you going the same direction? So you just color the functions with effect handlers and prohibit calling these functions from ordinary or not?
No, I think we don't want to color our functions, right? So this is the advantage of actually implementing them with call stack and not CPS, right? So we don't have to color our functions. We can call any functions from anywhere. We can, in fact, have we do not color our functions in our current implementation, right? And the way color sort of comes through is when you have an FX system, it might be the case that these sort of show up as inferred FX on the function type, right? So if you have a pure function which calls an effectful function, that function gets the effectful function type. It just means that you have to have a handler around it at the top, right? So that's the sort of way. This is sort of compositional, right? We are not placing restriction on what functions can call other ones, you just tend to get the effects that are performed by the functions that you call if you don't have a handle. So the strategy is different. Again, I wouldn't classify this as color, right? We don't. This is not like splitting the world. This is just tagging the functions with what they do. So, for example, right? So if you call a function which happens to perform an effect, but also handle it, externally it appears pure, right? Because any effects that it performs are handled by that function. So it just is a pure function at the point. But this is not true, if I'm not mistaken, in a colored setting, right? Color just pervasively goes through all the way.
Well, it depends. It can be either explicit. So in case of coroutines, we require explicit coloring. So you cannot call suspend functions from non-suspend functions.
Yeah.
But it also can be explicit. I don't have examples in mind right now, but the compiler propagates the color.
Right. Okay. I see. So I mean, this might be a sort of an orthogonal thing, but I did come across this project Loom for JVM, right? Which sort of gives you.
Loom, yeah.
So if you end up using Loom continuations, right, for implementing your asynchronous tasks, would that incur a lot of cost that is not acceptable for Kotlin, or what is?
Well, for starters, Kotlin should work on multiple versions of JVM.
Okay.
So
sure.
We will still use our CPS transformation.
Of course. Okay, that makes sense. Yeah, I think this color dichotomy is a bit. Once that color becomes part of the language, it's sort of it's pervasive, right? You have to sort of.
Yep.
I think we have that problem. Except that in your case, you have to work with the JVM restriction, right? You can't capture. I understand. I think that's the way to go. Yeah. Yeah, I don't have any clever answers that would circumvent this problem. It's just hard work.
So we just decided to give in and introduce code coloring as a feature.
Yeah, that's fine. I mean, in an environment where you don't have control, I think that's the thing that you have to do.
Thank you very much.
Yeah, very nice. Thanks for the questions.
Thanks, Casey. It was very, very clear talk.
Oh, thank you. Thank you.
I have a question about speed up, which you achieve by removing monods at all. Is it specific only about the monods which implement concurrency, or I can rewrite code with some random monad? I'm particularly interested in lazy stream monad, and if I rewrite, I could get some performance speed up. Rewrite using effect handlers. Did somebody studied this in a very scientific or small way?
I think we are. So, which monad did you mention? Sorry, I sort of missed that word.
Lazy stream.
Oh, I see. Okay.
For non-determinism, you have some examples in your slides.
Yeah. So. Comparing, so we have some results from the paper where we compared poor man's concurrency monad, right? So, and for some of the examples that we have on the paper, we are around 2 to 3x faster, right? So these are on very small examples. One of the examples was the generator, and other one is this toy example called Caminio's Redux, right? Which is like a benchmark program that all of the other languages also use, where they want to show the benefits of concurrency, we see sure benefits there. So and that was scientifically measured. Yeah, so I suspect that if you rewrite your monad to use effect handlers, you will see 2x performance improvement. That's my takeaway from having done these experiments. The main benefit comes from the fact that you're not allocating intermediate closures. Does it sort of answer your question?
Yeah, it is. Thanks.
Yeah.
Also, I thought a little bit about your way to copy in continuation, which should be multi-shot, but it isn't. Is it? Is this moment too error-prone if someone forgets to copy this continuation, and I suspect it will get some runtime error like unhandled effects or something.
Yeah,
Can it be fixable by fancy effect type system or something?
Yeah, I think there is a story there, right? So what you need is linearity, right? So if you have multi-shot continuations if you think about multi-shot as an effect, right, that cannot mix with linearity, right? That's the high-level takeaway. If you use linear resources, you shouldn't be using multi-shot in that context, because you might run it once, that might release the resources. The next time you might just release it again, and strange things might happen, right? So these sort of this cannot be just solved with the FX system, because we need to count things. This needs linearity. So yeah, so fancy FX system is not going to solve this problem, unfortunately.
Maybe you know some most promising linearity research about linearity, which can be implemented and retrofitted into OCaml.
Yeah. So there is Guillaume Munch from I don't know where he is now. He used to be at one of the Indria places. So he has a paper which talks about linearity. I think he calls it resource programming in OCaml. So he takes the ownership and borrowing ideas from Rust style and sort of adapts it to how we can include that in OCaml-like language. Specifically, he also mentions linearity in Multicore OCaml continuations, right? So that is he has that paper is like well thought of. Somebody has to go ahead and implement it. But it's a quite complicated system. It's not an easy one from what I had seen.
Who is author? I forgot.
Let me write down the name. Guillaume Munch. His last name is double barrel, but this is.
Thanks. I see. I will Google it. Thanks.
Okay. Yeah. So he has a very nice paper which sort of describes this in detail. The last time I looked, the system was more complicated than what I would like to program with in OCaml. But anyway, it might just turn out to be that complicated for the benefits. But it can be done, is what Guillaume tells us.
Thanks. Maybe somebody else also has a question.
Any other questions? I'm happy to stick around and answer questions.
I'm almost sure it is the end for today.
Okay.
We are very truly happy to see you again somewhere, maybe next year when you have a new PGI 2022 paper or even bigger paper.
Yeah, so the next waiver might just be the effect system, right? So that'll be exciting.
Maybe it
Anyway,
will
thank
be
you.
even in OCaml already. It would be
We'll
great.
see. That's what we are working towards, right? So we'll see. It'll eventually happen. But yeah, but paper, yeah, certainly. Thanks for inviting me to give a talk. I really enjoyed the questions and the interactions. All right.